I'm going to talk about discrete optimization for multi-agent pathfinding. And really, two new approaches have been developed at Monash University. Brian Gange is the leader of the first one I'll talk about, and Edward Lamb led the second one. But Joanne Lee, who's also highlighted there from University of Southern California, has worked with us on this problem. And there's a lot of crossover and interaction between the various different approaches to tackling this problem. So she's probably the leader of the third best technology, the third of the three the best technologies we know for this problem. So here's an outline of the talk. I'll talk about multi-agent pathfinding and what it is. Then I'll talk about a CP approach to tackling multi-agent pathfinding, and then a mixed integer programming approach for tackling multi-agent pathfinding. And then I'll conclude and talk about the problem in general. Okay, so what's multi-agent pathfinding? It's this problem where we've got a map. It's a grid map. We're going to stick with grid maps for the moment, although it doesn't have to be a grid map. And it's divided into cells, and the cells can be passable or obstacles. So the white cells are passable and the black cells are obstacles. And you're given a set of agents, and they have a start location where they start now, and they each have to go to a target location or an end cell. And they all have to move there. So in every time step, an agent can move north, south, east, or west, or it can just wait where it is. And then the important problem that makes it hard is the agents interact with each other. So if two or more agents cannot occupy the same cell at the same time. So if they try to move into the same cell at the same time, then that's a collision, a vertex collision. And another thing that can happen is you can have this edge collision where two agents try to use the same edge between these two locations at the same time in opposite directions, right? They couldn't use the same edge in the same direction. They'd already ever had a vertex collision if that had occurred. All right, and then the usual aim in multi-agent pathfinding is to minimize the sum of the individual costs. So that's the sum of the path lengths of the agents, and that's because that gives you the biggest throughput. So there's an alternative objective where you can just minimize the makespan, so minimize the maximum of the path lengths. It's typically an easier problem to solve, and it's not the one that we care about the most in the study of this problem, although I'll talk about it a little bit on the side. And the assumptions I'm going to make for this talk are we've got a centralized solver, so we've got one, we're going to plan all the agents together. It's an offline task, so we're going to do this plan once, and we're looking for an optimal solution. So why should we be interested in MAPF? Well, actually, MAPF occurs in a lot of problems. So in robotics and video games, transport applications, production assembly. But the one that's really motivated its use nowadays, most importantly, is in warehouse logistics. And so modern fulfillment centers have hundreds and hundreds of robots running around, and they have to not run into each other. And so this is why this problem is of particular interest nowadays. Okay, and the other thing good about this, the problem is it's the quintessential multi-agent movement coordination problem, right? So the real world problems of real robots are harder, but they always basically have this underlying problem. And indeed, in the warehouses, they use a grid map representation to represent their robots just to plan things, because it's much easier than using arbitrary 3D and the robots move on a grid. It's NP hard, which is not surprising since it looks like it's complex. And so then the question is, well, why would you need optimality? So one thing about optimality is the problems that arise for the optimal version also hit the bounded suboptimal case. So if you even don't want an optimal solution, you still need to understand getting an optimal solution, because you're going to have to solve the same problems if you want a bounded suboptimal case. And there are some unbounded suboptimal solution approaches to this problem. If you make certain restrictions on the problem, there's some polynomial time algorithms which will find your solution, but they're very, very bad. They tend to be very, very bad sum of costs. Okay, so let's talk about MAPF solving methods. So there's the A-star method. So this problem comes from the planning and search sort of community. So they tend to use A-star as their tool to tackle any kind of search problem. Conflict-based search, which I'll come back to, which is basically the state-of-the-art approach before we started this work. Encoding and reduction. So you can encode this problem into Boolean satisfiability or answer set programming or constraint programming or mixed integer programming. And there's suboptimal methods, which we won't talk about, which can tackle the problem, but if they're bounded suboptimal, then they're typically close to the kinds of methods we'll talk about now. And otherwise, these push and swap style methods, which I talked about briefly, are polynomial time, but give you extremely bad solutions. And interestingly, even though they're polynomial time, we have faster solutions using some of the methods I'll talk about today. So it shows you've got to remember that this asymptotic complexity doesn't necessarily tell you everything about what's going on in the problem. All right, so let's think about the basic A-star approach. So the basic problem with the A-star approach is we've got n agents who can be in each of V locations. So if we're talking about the state at any one time, we basically have to have this vector of the n locations, right? So the state space is rather large. And the operators then I can move each individual agent. So I move all the agents together in lockstep. So basically I'm moved from one state to another state. I can have a heuristic function which can just look at the shortest path from each agent to its goal, and that gives me a pretty good heuristic. But you can see even for this tiny example where I've really got 2m nodes in the graph, plus a few more, there's m squared, at least m squared state space, right? Because these two mice have to run through the bottleneck at C, and in the first step, they got lots of choices. They got m choices each, which would each be optimal to get to C. So we get this explosion in state space, and that's the problem. So the solution is conflict-based search, which, assuming you're a discrete optimization person, you might recognize it's a kind of Bender's approach. So we're going to plan each agent individually, and what we're going to hope is they don't conflict, and then we're finished, right? But if they do conflict, then we'll look, if we have a pair of agents whose current plans conflict, they use the same resource at the same time, t, then we're going to split the problem into two. In the left child, agent A cannot use x at time t. In the right child, agent B cannot use x at time t. And then we'll end up with two children. We'll pick one subproblem to work on, and that will either be solved or we'll split again. We keep going. Replan the affected agent, enforcing the constraints now that it doesn't use the resource where it's not allowed to. And this continues until we find a node where none of the plans conflict and we're finished. So let's have a look at an example. So here's our initial plans. You can see that the first agent goes from A1 to C to G1. The second agent goes from BM to C to G2. And we've got a conflict at C2. So we're going to split. We're going to say, okay, on the left branch, we're not going to allow the first mouse to use location C, which is the conflict location, at time 2. And then we'll replan that mouse, right? And see, here we can replan the mouse. It goes to A1 and it waits for a turn, so it just stays there. And then it goes to C at time 3, and then it goes to G1 at time 4. And you can see we've removed the conflict, right? And we've actually found a solution. And if we did the same on the other branch, we would find a solution by delaying the second mouse. The problem is that it won't try this first, right? Well, it will, in this particular problem, it'll be okay. But you can see that if I looked at all the different possible paths through C, if I didn't notice that C was the bottleneck, then I could try a lot of different paths. Okay, so that's CBS, which is, before this work, the current state-of-the-art approach to MAPF. So of course we can do encodings and reductions to various discrete optimization technologies. So for MIP solution, it's a multi-commodity flow model. It works for small graphs and less than or equal to 50 agents. And that was for makespan. It's a bit harder for sum of costs. There's a SAT solution using sum of costs as the objective, and on small maps, and actually on small maps, it can beat CBS. So one thing is true, that on very small type maps where it ends up being more like a pebble movement problem, where there's very few spaces, like the 16 puzzle, right? You can think of that as a multi-agent pathfinding problem. It's more about where the gap is and where the agents are, and these encodings can work there. There's a CP solution where the variables are choosing a path for each agent, and that'll tie in with what I'll talk about in the second half of the talk. So they have this dynamic variable domain that was also for makespan only. There's a SAT modulo theory solution for some individual costs. So basically this is the same as the SAT solution, but you lazily construct the SAT model. And it's better than the CBS on type maps again, and small numbers of agents. And there's an answer set programming solution, very similar to the SAT one, uses unsatisfiable clause-based optimization, which is what we'll talk about in the first part of this talk, the first part of the technical part of this talk, again for small graphs and small numbers of agents. Because the problem with any kind of encoding and reduction is any naive encoding is going to have this problem. You need a variable like x apt. Agent A is at position P at time T. And the number of variables here is n vt, right? So you've got n agents, v vertices, and t is a time limit, a time bound. And you end up with too many variables even for the smallest cases. So for our example that we looked at with the 2 mice, you end up with this number of variables, 2 times 2, n plus 5, which is the nodes, times 4, which is the minimum amount of time you need to solve the problem. And indeed, finding a tight time bound is hard to determine, and it's order v cubed for the sum of costs objective that we're talking about. So you can see that gets to be very big if we just use this relaxed time bound. All right, so let's look at a different approach. So let's look at a constraint programming approach for tackling MAPF called lazy CBS. And Graham Gaines is the principal implementer of this, or the innovator, I guess, who thought of this idea. So the thing is, CP is an integrative solving approach, right? So we can hide subproblems inside global constraints. So what we're going to do is essentially re-implement CBS inside a CP solver. And then you're going to say, well, what's the advantage? Well, the advantage is we'll be able to use no-good learning, and we'll see how that'll make a big difference. So let's look at lazy CBS. So here's an abstract sort of CP model of the problem. We've got a set of agents and a set of locations. We've got a maximum time that we're allowed. So time is just the 1 to max time steps. The data we're given is for each agent its start location, and for each agent its end location. And then we'll have a variable, which will be the only variables here really, or the main variables here, which is telling me the cost of each agent's path. And we're going to minimize the sum of those costs. That's the sum of individual costs objective. We've got these permitted variables, right? For each location, for each time, which agent is allowed to be there. I'm going to ignore edge collisions for the purposes of the talk, just to make it simpler. But you can say, we know that for every location for each time, only one agent can be there. So we can say which agent is permitted to be there. And then we're going to have everything stored in one big global constraint. And this is for each agent, we're going to say, what is the cost of path for agent A from location start of A to end of A, satisfying the permitted constraints, and C of A is that cost, okay? So basically we've hidden all of the hard part of the problem in here. So we're going to build this cost of path propagator to update path costs. So what is the role of this thing? It's meant to update the lower bound on the cost. That's its only role. It doesn't care about the upper bounds on the cost. Just make sure it can make this reasoning about the lower bounds. And so how do we do this? Well, we compute the shortest path from start of A to end of A that satisfies the permitted constraints, right? So that if you use some location P at time T, so P of T at time T, then agent A is allowed to use it. And then we'll enforce that C is greater than or equal to the length of that path, right? And we know that that's a correct inference, right? If the shortest path from start of A to end of A is at least length P, then there's no other path that satisfies the constraints, then there's going to be no path which can be shorter than that. So we should update the permitted, right? Because we're going to use a whole lot of locations at various times on that path to ensure we get no resource conflicts, but we're not going to do that, okay? So just like in CBS, it's a style of Bender's approach, we're going to let that happen later on during the search. So essentially it's exactly the same algorithm as the CBS individual agent pathfinder. It's just hidden inside a propagator. Okay, so aren't we cheating? If we look at our model, we've still got this thing of size for NBT. So if we look at this array, which location, time, a variable agent, it's the same size, right? So we haven't got rid of the size problem, but we're going to be able to get rid of it by lazily creating the permitted variables as required. And this is essentially the same idea as what happens in CBS, where we only consider, we only add a constraint about a location once we see that there's a conflict there. There's another bonus here that you don't need to reason about max time any longer, because we'll just add location permitted constraints wherever things happen, and the max time is irrelevant. Okay, so a permitted variable is only required when two variables use the same location at the same time, and so that's the only time we'll do it. As I said, this is exactly the same as CBS. Okay, but then it looks like we just re-inputted CBS. Well, it's not the same, and I'll show you that. So CBS uses best first search because it's using A* to pick the best node, the best looking child node to explore next, because it's trying to quickly get to the optimal solution. Lazy CBS is using lazy clause generation, so it's using depth first search, which might seem like a bad idea, but because learning is possible, it's going to be able to avoid repeated work. So let's have a look at one of the major weaknesses of CBS. So here we've got two independent conflicts. You can see the purple and the yellow agents are going to conflict somewhere along their path, and the green and the blue agents are going to conflict somewhere along their path. And if we look at a CBS tree for this, we'll pick, let's say, the purple yellow agent, we'll split, we'll make a conflict. So we'll say, okay, X is the U space is where the X is. We'll allow the purple agent not to use it, or we'll allow the yellow agent not to use it. Okay, if we go down the branch where the purple agent doesn't use it, we'll find a solution by delaying the purple agent one step, and then we'll find this problem with the blue and the green agent. And actually, either of those leaf nodes there would be a solution where we've updated the lower bound to get the best possible solution. But unfortunately, in A* search, the unexpanded node with the dashed lines looks more promising, right? Because it has a cost of only 1 at the moment. So a delay of 1 from the minimal possible costs from the start. And so we're going to expand that node, even though if we expanded either of the other nodes, we'd actually have solved the solution. And the problem is when we expand that node, we're going to find exactly the same conflict between green and blue. We're going to do exactly the same thing again and again. And it's going to end up, we see this behavior all the time, that we basically end up exploring the same conflicts many, many times in multiple parts of the search tree, right? Because these two conflicts are completely independent. So actually, we sort of would like to separate those search trees out. All right, so let's talk about how we're going to do the search in lazy CBS. So in fact, CP solvers are astonishingly bad at optimizing the sum of objectives like we have here, sum of path costs. But luckily, there's a new approach to optimization coming from the SAT world called call-guided optimization. And what this is, you assume the best possible solution. So each path cost is its shortest path. And then you find a contradiction. And then you rewrite the objective with that knowledge of the contradiction. And then you again assume the best possible solution under this new rewriting. And you repeat this until a solution is found. So it's basically a failure-driven search. But in order to do it, we need to get an explanation of why our search failed. And that's what lazy CBS is going to give us. So we need to be able to explain why is a path too long. So if you look at this example, we've got a start location S1 and a goal location G1 for agent A1. And we've been given a bound that the cost of the path is less than or equal to 5. And now we end up finding there's no possible path. So how do we do that? We start a backwards search from G1 at time 5, because we know we have to arrive there by time 5. And we find what resources are blocked. So we find that even though there are 4 blocked places, the black node is also being blocked at the appropriate time, only 3 of them are visible from the goal, right? Once we reach the V is blocked and W is blocked, we can't get to the other black location. So we mark all these blocked locations from the goal. And then we search from the start at time 0, and we treat unmarked conflict resources as usable. We don't treat them as if they're there, and then we collect all of the marked block resources. So basically, we find that the blue, only the V and W resources are what's stopping us getting from S1 to G1 in 5 steps. And you can check it yourself. Once you block those 2 resources at the right times, at time 2, both of them actually in this case, then I can't get to G1 in 5 steps. I have to wait at least once somewhere. And so I get this explanation saying that because of these 2 blue resources, the path length for agent 1 has to be greater than 5. Okay, so that's how I explain an individual path. So now let's have a look at lazy CBS in action. So here we have 2 agents. We initially constrain them to have an upper bound no greater than their shortest path, so they can get there in 9, each of them, right? Blue to blue and purple to purple. And then we run some paths. So there's a few optimal paths. We just pick one for each of them, and we find we have a conflict, right? A conflict location. They both reach that location at time 5. Okay, so we introduce a permitted variable for that overloaded resource. So that's location U at time 5 can either be given to agent 1 or agent 2. Now, on the left branch, we say, well, agent 1 is allowed to use it, so it keeps its path, but agent 2 has to wait. It can't get there in 9 anymore, right? So because it always needed to go through that one at time 5 to get there in time 9. So we end up with a path which is at least 10 long. Okay, and then when we try to explain this failure, as I talked about just a moment ago, we find that because it's not permitted to use location 5 at time, location U at time 5, so the agent there is not 2, then the path length for 2 has to be greater than or equal to 10. And we try the other branch. Okay, on the other branch, we set who's the agent permitted to use this location is 2, and here we find the same problem for agent 1. Right, agent 1 has to wait somewhere. It can't get to its solution in 9 time steps. So we get this explanation of why the failure is saying, well, if agent 1 is not allowed to use U at time 5, then its path has to be greater than or equal to 10. And then we do some resolution on those 2 things, and we find that, okay, either C1 is greater than or equal to 10 or C2 is greater than or equal to 10. So we've learned a no good that's independent of all the other agents, right? So we know that this is true. We didn't look at any other agents. We know that one of agent 1 and 2 has to take at least 10 to get to its target. All right. So let's see it in action in general on this bigger example. So we start off, everyone starts with their shortest path. So we have a lower bound of 44, so all the shortest paths here are 11. And then we assume that everyone has to take its shortest path. So we set all of the length bounds to be less than or equal to 11. So basically, if that holds, if we get a solution like this, then that's the best we could possibly do. It must be optimal. And we're going to reason first on the purple and the yellow agents and say, well, actually, we're not going to find this no good. At least one of them has to take at least one more step. So we had this no good that C1 is greater than or equal to 12 or C2 is greater than or equal to 12. Now I'm going to rewrite the objective. So the current objective is basically saying the sum of C1 plus C2 plus C3 plus C4. I'm going to basically say, well, look, I know that that sum has to be greater than or equal to 45 now, because at least one of C1 and C2 has to be greater than or equal to 12. And I'll actually add a Z variable, Z1, which counts the number of them which are greater than or equal to 12. So I'll relax both of the bounds on C1 and C2 to be greater than or equal to 12, right? But I'll enforce using Z1 that only one of them can be equal to 12. The other one has to be less than or equal to 12. Otherwise, this bound in Z1 is less than or equal to 1 will be violated. So I'll allow exactly one of them to take that length 12. And we've got a lower bound of 45. Then, with these assumptions, we'll run. We won't get a problem with the yellow and purple because one of them take a length 11 path, one will take a length 12 path, and that'll meet all the constraints. We will get a problem with the C3 and C4. So just analogously as before, we'll find that one of them has to take a path length of at least 12. So again, we'll do the same trick. We'll relax both of their upper bounds to be 12, but we'll add the Z2 variable, which forces that only one of them is allowed to be 12, the other one has to be 11. Otherwise, this Z2 bound would be violated. And we'll find a lower bound of 46. And indeed, now we have a solution of 46, and so we've actually solved our problem. Okay, so that's a lot of work. It's optimal. Seems like a lot of work, and you go, well, those were clearly independent. We could have just separated out the problems because they never went close to each other. And there is some work in CVS on doing independence detection. You can split agents into sets that never interact. The problem is, and then you can solve the MAPF problem separately, that's good. The problem is the number of agents grow, basically nothing is independent. And if I just add this red agent, which goes across the map, it interacts with all of the other agents and it joins them all together. So independence detection completely fails, even though this red agent doesn't really change the underlying problem. The blue and the yellow agent, the blue and the purple agent have a problem, the green and the blue agent have a problem, and there'll be a problem with the red agent as well. We can still learn those independently using a learning solver, as we've done with lazy CBS. So if we compare it to CBS, it's close to iterative deepening CBS, which is a rather new variant of CBS. Interestingly, each solve essentially explores a whole CBS tree because it's doing that in order to build this nogood. But the good thing is that nogood is globally true, will be true forever. So the branches on the permitted LT are very analogous to CBS branches, and there's a cost. We do many more high-level nodes in lazy CBS than in CBS. We lazily introduce the permitted LT variables, and by the time we get to a leaf node, all of the existing permitted LT variables have to be fixed. And then we can either find that we found a solution or that there's a new conflict between two locations at location L and time t. We add a new permitted LT variable and branch on it, which is analogous to what's happening in CPS. But once we've added that variable, it stays there, and if we restart, we find a nogood or restart, we'll have that variable around from then on. And the path propagators are exactly analogous to low-level search in CPS. But the big advantage is the nogoods that we generate are universal, and they prevent repeated work across subtrees, and they prevent repeated work in resolves, because we'll also generate lots of nogoods about other stuff. And then when we start a new resolve, once we've found a failure, we won't repeat that work either. And so that ends up with our learning, remembering all the problems we've seen before, we exponentially reduce the search space. So just to show you some brief experiments, so if we take lazy CBS here compared to two variants of CBS, so here is on a 20 by 20 map with 10% obstructed edges, you can see that lazy CBS is far beyond the other methods. And this is exactly because most of the time, these methods end up solving the same problem repeatedly on different branches of the search tree. And lazy CBS avoids that and does much, much better. If we take a much bigger map, okay, so here the ECBS, right, so this is the bounded suboptimal, actually avoids most of the problems because on a bigger map, the shortest paths are longer, which means that the 1% bound gives you a lot of flex, and you can basically avoid most of the problems here. So it turns out if you've got a big enough map and few enough agents and enough flex, then these bounded suboptimal methods can easily find solutions. They avoid part of the problems, but I'll talk about one of the problems, that what's causing lazy CBS to be slower here compared to the other example. In fact, that's rectangle constraints. So rectangle constraints were recognized about 2 years ago as a critical thing that you need to take into account when you're solving MAPF problems, at least optimally. And once we take those into account, so that's lazy CBS plus R, then we can get similar behavior to the ECBS case for this easy problem, essentially. I'll come back and talk a bit more about rectangle constraints in the second half of the talk. Okay, so let's look at a mixed integer programming approach to the same problem. So what we're going to use is branch and cut and price. And for those of you, many of you, I guess, in this audience will know what it is, but it's a very complicated way of solving a mixed integer program, if you want, by lazily constructing the linear model during solving. It's guaranteed to find optimal solutions, and it allows us to avoid the problem of too-big an encoding, which of course is exactly the problem that we've got here with any kind of naive approach to MAPF. Okay, so here's my short form version of branch and cut and price. So we have a linear program Okay, so linear constraints with a linear objective, and we're going to solve it by the simplex algorithm. Then we make that into integer program by making some of the variables take integer values, and that's solved by branch and bound. And then branch and cut and price is a generalization of branch and bound, where we're going to start with a very small matrix, so with very few rows, that is constraints, and very few columns, that is variables, and add them in as we progress the problem. So if think about a simple example here. So here's a polytope, and like the simplex method would say, okay, I start here at the 0, 0, 0, that's where simplex starts by default. If I'm trying to optimize sort of coming out of the page, then I'll try to move along an edge as far as I can. And I'll get to that vertex, and then I'll see if I can move further, or move along that edge to get to that vertex, and then I'll say, oh, I can't get any better, and that's the optimal solution. So what's a branch and cut and price approach to the same problem? Well, essentially, it says it starts with no constraints and no variables. So it needs it'll say, well, if I had this variable, I could move in this direction. Okay, so it'll move infinitely far in that direction because it's got no constraints. But then we'll say, well, hang on, we can't move infinitely far. We'll add a constraint to stop you moving infinitely far in that direction. And then we'll find a new direction that's interesting to move in. And then we'll move in that direction. We'll find, hang on, no, there's a constraint which stops that. And then we'll say, okay, now I can't find any better solution. So I actually proved optimality without even introducing the third variable. And that's the sort of idea. Of course, this is a tiny problem that I can show you on the screen, but we're going to talk about a linear programming model with an exponential number of variables. And it's going to be very key that we don't have to introduce them all in order to know that we've got the optimal solution. All right, so let's look at a BCP program algorithm for MAPF. So the master problem is I'm going to select good paths for the agents using an LP relaxation of the problem. The pricing problem is I'm going to find better paths for each agent using A star. And the separation problem is going to check for collisions along the selected paths and add in constraints in order to avoid that. All right, so our problem graph we have, so here's all our NVT size objects. We have each vertex and each time, right? And then we have an edge between two of these vertices, so that it's both a cell and a time pair, right? And so you can either go north, south, east, or west, or you can stay where you are. So the time in the second vertex is always the time in the first vertex plus 1. And then a path is a sequence of vertex such that the adjacent vertex are adjacent. Okay, so our master problem is for every agent, right, we're going to assume a set of all possible paths. We're going to pick the best path for each agent. We're going to pick a path for each agent, or we're going to pick a proportion of that path, somewhere between 0 and 1. Obviously, these are integer variables, so in the end, I want them to be either 0 or 1, so I'm going to pick exactly one path, but we're going to relax them, so we actually pick a proportion of the path for each agent. And then we're going to add vertex collision constraints when we see that a vertex is used by at most more than one agent at a time. We're going to add edge collision constraints when we can see that an edge and its reverse is used by more than one agent at a time. Okay, but of course the number of paths there, so here's the master problem in all its glory, right? We're going to minimize the total cost. We've got for each path, the selected path, we get lambda p times that cost. We're going to, of course, select exactly one path for each agent. Then for each vertex, we're going to have this constant xpv, which says that this vertex is used by this path, all right, at this time. So a vertex is a cell time pair. So we're going to make sure that it's only used at most once. And for each edge, we're going to make sure that each edge and its reverse is used at most once at any time. Okay, so this is a huge model, right? Because there's an exponential number of paths for a start off, and there's a huge number of constraints here. And of course, what we're going to do is not solve this master problem, but restrict it, right? So we know that most of their paths are completely useless. This red path here, which goes round and around and arrives at the target, is much worse than the green path, which just goes straight there. So most of the paths are never going to be very interesting. So our whole point is to start off with a very small set of paths and just add new paths if they could make our solution better. So restricted master problem starts off looking like this, right? So we basically have, so P prime A is the set of available paths for each agent. And we're going to just say each agent has to select at least a total of one path from its available paths and no other constraints initially, right? So we can only have one path for each agent if we want, just their shortest path. Then it'll be easy to solve the initial restricted master. So then what will happen? We'll find a solution to that and then we'll check, right? We'll check the sum for every vertex. Remember, that's a cell time pair. In the current solution, do we use it more than once, right? So if we do use it more than once, we're going to add the constraint that we saw back here. Right, this one, the second set of constraints for vertex, for that particular vertex location. We'll add it in, right? So similarly, we can do the same for edge conflicts. We'll check if we use an edge more than once in the particular solution we've picked in the LP solution. If we do, we're going to add this constraint as a separator and get rid of it. All right, and the hard part is the pricing problem, right? So we've got a current solution to our linear programming, and that's going to give us dual costs on each of the shared resources and shared vertexes. And that'll end up basically converting into costs in a shortest path problem. So we'll look for a path which is minimizing this reduced cost version of the shortest path. So CP is the normal path length, but we're paying penalties if we're using, so all the dual variables are negative, so we're basically going to add to that minimum cost if we use shared resources or shared vertices or shared edges. Okay, so we'll look for a path, and if we can find a path that can get this CP less than 0, then we can improve our master problem. So this is the usual column generation style approach. The nice thing is this is a shortest path problem, so we can solve it just the same. All right, so that's the reduced cost calculations. You can see, so here the difference is that whether we use this resource or not is part of the decisions that we're making, whereas in the master these are fixed because the paths are fixed. Okay, but that's not enough because, of course, the LP is going to pick half of this path and half of another path. And it actually is, it will try to do that very often because that's often a way of avoiding overuse, right? If I have two places to go through, I can each use half of it in both directions and then there's no conflict. So we have to remember that we need these variables to be 0, 1 in the end. So we're going to select a vertex that is fractionally used by some agent A, and we're going to branch on. Either it must visit that agent, that vertex, or it cannot visit that agent, that vertex. And we can do that by setting lambda p to 0 for the paths which don't satisfy the various conditions. So that's the branching. So one of the difficult things in branching cut and price is you have to make a branching which will work with your relaxed problem. And here this does the trick. Okay, and so that's our BCP, right? It iteratively calls 3 subproblems. Restricted master problem, okay, so that selects the good paths from the paths we have available. Each column represents a proportion of the path selected. So we have this lambda p is a 0, 1 variable, 0, 1 continuous variable. And the row represents the conflicts that we've added, and they're all satisfied in the LP solution. Then we look at the pricing problem. We try to find better paths for each agent using ASA. Well, actually, typically we'll do the separation problem first. We'll check if this selected set of paths actually have collisions in some other locations that we haven't thought about, we haven't added constraints for. We'll add that back in, resolve the master until we finally find a solution to that. And then we'll solve the pricing problem saying, okay, for each agent, we'll look, is there a better path, a path I could add which would give me a way of improving the current LP solution. Okay, and finally, the master problem will end up with fractional proportions of paths, and then we'll do branching, right? And that's the branching part of branch, cut, and price. By branching on this agent vertex thing. Agent must or must not use the vertex. Okay, So that's the BCPB, the basic version. We'll talk about some improvements because it turns out, actually, very disappointingly, the basic version of branching cut and price doesn't do that well, and you'll see it in the results. Okay, we're going to have to add 2 classes of redundant constraints, and we'll add a new kind of branching rule to help us get there. So one of the critical things that was only noticed in 2019 is rectangle symmetry. So if you look at these 2 agents, A1 and A2, A1 has to go from where it is now to the red dot, to the blue dot, A2 to the red dot. Then what happens is, you can see in these paths here, whatever happens, they end up conflicting somewhere in that grayed rectangle if they take their shortest path, right? Every shortest path for A1 and every shortest path for A2 will intersect somewhere in that grey rectangle. And this is a real problem for CBS because it takes an exponential amount of work for CBS to work out that there's no way that they can each take the shortest path, right? And the same thing happens in BCP, right? So the way we solve this problem is we say, well, the number of times you can cross into and out of this rectangle has to be less than or equal to 3, which means that someone can't go in and out at the optimal time. So here you can see we've marked all the edges by the optimal time when an optimal path from A1 to blue or A2 to red would to go through that edge. And we say, okay, only 3 of these things can be true. Because if we know that if we send both agents through at optimal, there'll be a conflict somewhere in the middle. And this is nice because this actually works for fractional paths. So if we send A1 half down one path and half through another path, and A2 half through one path and half through another path, we won't see any individual vertex conflicts if we pick those paths correctly, but there is still the rectangle conflict, and it won't allow this because if we add up the total amount, we'll just get a 4, even though we're using 2 half paths. Another important kind of conflict, which is also now used in all of the various technologies for MAPF, is corridor conflicts. And this is where 2 agents have to cross each other in a narrow corridor. And so the MIP solution to this will say, well, A1 will move towards each other, and then they'll split into a half agent, and half of A1 will go forward and half of A2 will go forward. So they only use 1/2 of the edge at that time, and we only use half each of the 2 vertices at that time. And then the rest of the agent comes across, and basically you have a half distance. So you have this fractional corridor conflict. So you can also add separation to avoid this fractional corridor conflict by basically counting how many agents across this L1, L2 boundary at either T1 or T2. So at now and one after the time, because the LP solution will naturally find the solution as a way of avoiding any individual vertex conflict or edge conflict in this case. Okay, and the final trick we're going to need to add to make this work is branching on path length. So this is a way of avoiding agents taking fractional paths, essentially. So imagine agent 1 has selected paths C1 to C5, right? So the first path at proportion of half and the next path at proportion of half. So its cost looks pretty good, it's 5.5. Now we're going to branch and say, well, we're going to force it to be less than or equal to 5 or greater than or equal to 6, right? So we wipe out the ability to use the second path, and now its cost is less than or equal to 5. On the other branch, it's greater than or equal to 6. And so this forces, basically by fixing the path length, we don't force a single path to be chosen. We stop this behavior, which is very common in these LP solutions, where you sort of move an agent along, then send half of it forward one step and then follow it at half, because that's a way of avoiding using any resource at total 1 at any time. By branching on the path length, we stop. Okay, so to sum up, BCPB is our basic branch and cut and price with vertex and edge separation, the pricing problem solved by A star, and branching on agents using this vertex location time, or it doesn't. BCP adds the rectangle conflict cuts, the corridor conflict cuts, and first it branches on path length. So any agent that we first essentially fix the path length of an agent before we start branching on vertex time locations. So experiments. So we're looking at some standard maps from the MAPF world and comparing with CBS. So without CBSH is the best CBS version, and RM includes handling rectangles. So you can see on the 20 by 20 open map, CBSH RM is very good. So you get a lot of rectangle conflicts on an open map, and CBSH RM is much, much better than CBSH. BCPB, you can see the basic version was actually worse than CBSH, but once we improve it, we get much, much better. So rectangles were killing us even worse than they were killing CBSH. Once we add obstacles, then it gets harder, and in fact, you can see that the RM starts to lose out. Its advantages are gone. There's not so many rectangle conflicts, and it's just this repeated work, which we're avoiding in the branch and cut and price approach. Then we get to a much more complex map, and you can see that the BCP version is much, much stronger. And in fact, it closes many, many instances that were open for this problem. And there's been some subsequent work improved further. And one of the interesting things you see when you look at the behavior of BCP is actually the lower bound gets pushed up very rapidly to very close to optimal. So it's a very good method at pushing the lower bounds up. Right? So the LP relaxation with the cutting planes is actually doing a good job of pushing that lower bound up, and then basically we just need enough branching to force to find a solution at that lower bound. So if we compare it to CBS, well, it reasons about all conflicts and agents simultaneously. That's what the LP master is doing, so that's really powerful. It uses paths anywhere in the high-level search tree, right? So if we generate a path, then it's always in the master and can be reused on some other node in the high-level search tree. You can extend it with other types of conflicts. So we've seen, you get, of course, the advantage of MIP. The MIP solver is very powerful. It's got a lot of sneaky things in it, and those you get to use. It's anytime, although it's not very anytime. It tends to find the first solution. It can find a first solution before the optimal, but it usually doesn't find it that much before the optimal. And you get this very tight lower bound, even if no feasible solution is found. Okay, what is it bad? Well, it's branch and cut and price is difficult to understand for many people who haven't dealt with it. It's certainly difficult to implement, right? 2,000 lines of code for A star, but 12,000 lines of code for the separators. And of course, we're not counting all the code inside the MIP solvers. So in conclusion, a straight CP solution to MAPF doesn't scale, but lazy CBS does. Essentially, it's a Bender's decomposition, right? We're using lazy variable addition, and core-guided search allows us to very quickly move towards optimal. It's just like CBS, it only finds the optimal solution, doesn't find any solution before that. But because of core-guided search and nogood, it avoids doing a lot of repeated work. Similarly, the straight MIP solution doesn't scale. Branch and cut and price, of course, is a dancing wolf decomposition of the problem. You generate these specialized column generators, which is a low-level pathfinding with arbitrary costs rather than just unit costs. You can add specialized cuts for the kinds of things that go on. And in fact, I think Eddie has like 16 different cut generators now in his most recent version. But overall, one thing that's good, and probably not a difficult message for this community, but I've given this talk to the search community as well, is discrete optimization is very good at NP-hard problems. So if your problem is NP-hard, you should consider looking at discrete optimization techniques. And even though straight out of the box they may not work, there are lots of decomposition approaches that we can use to make things work. So here we've used Bender's, Danzig-Wolf. We haven't used Lagrangian. You can use logic-based Bender's, subproblem encapsulation, and CP, which we've done here. So there's an arms race in this MAPF sort of solving where methods from path planning and discrete optimization cross over. So rectangle symmetries were originally in path planning, and low-level search techniques from path planning have all been stolen for discrete optimization because we use low-level search either in the column generator or in the conflict resolver, the explanation as to why things can't be done. And this other information goes the other way. So corridor symmetries were first noticed by Eddie when he was building his BCP solution. Disjoint splitting is a natural thing that you do in discrete optimization search. You would never think about leaving both two solutions which appear in both sides of a split, but the CBS split does that, right? It says, in one side it says agent A1 may not use the resource, and agent A on the other side says agent A2 may not need this resource. So that means solutions where neither of them use the resource are in both sides, which means that you have duplicated work on both sides. And we're using depth first search rather than best first search, although of course that's a question about which discrete optimization technology you use as to which you prefer. And last but not least, I think one of the most interesting things about this is that call-guided search basically gives you a plug-in replacement for A*, right? So if you've got some kind of combinatorial state space and poor heuristics and repeated subproblems appear, then you should think about whether you can do what you're doing with call-guided search versus A*, and you might be able to do a lot better. And I know, because I've talked to planning people after seeing this talk, they're very interested in this idea because they use a lot of A* approaches, what they're doing, and they're missing out on that no-good learning. And so the idea of being able to use call-guided search to get there may help them as well. All right, that's the end. Questions?